All right. Hello, everyone. Welcome to the seminar. So today it's my pleasure to introduce Ling Sun, who's from Australian National University. So Lily is, as you can see on the bottom there, an expert in gravitational waves, and is a member of OzGrav as well as the LIGO, Virgo, CAGRA collaboration. So Lily initially did a BSc and an MSc in engineering, actually in Shanghai, before spending a few years as a software engineer. But then in 2014, she came to Melbourne to do her PhD in physics, and then moved to be a postdoctoral scholar at Caltech in the USA. And she's now research fellow at the ANU, where she's a member of those aforementioned collaborations. So thank you again for agreeing to give this seminar, and why don't you take it away?
Okay, thank you very much. So thank you very much for inviting me to give this presentation. And so as mentioned, I'm a researcher from OzGrav ANU and working on gravitational wave analysis in the LIGO Virgo CAGRA collaboration. And particularly my topic today is about probing ultralight bosons with black holes and gravitational waves. So I guess I haven't met many of you in the group, but I guess many of you might share a similar interest in this field. So I'm really glad to have this chance to talk about this work. Does this work? Okay, so to start with, sorry. Okay, can you see my cursor? Something weird going on my end.
Yeah, I can see the cursor. Yeah.
Okay. Good. So just to start with, I'll give a few words about gravitational wave detections and the major types of gravitational wave sources. So as you know, in recent years, gravitational waves from these mergent compact binaries have been directly observed on Earth by the detectors like the two LIGO detectors in the United States and Virgo in Italy. And also we have the CAGRA detector, joining the network recently. So in the latest, the 3 observing runs, with the last one ending about 2 years ago, we have now in total observed these 90 events from the compact binary mergers. So these newly discovered stellar mass black holes and neutron stars are all plotted on this chart. So with the size indicating their mass, these stellar mass black holes, you can see they have slightly different mass from those observed in EM channels. Some of them, actually fall in this mass gap, and we don't even know if they are black holes or neutron stars. But these are not the only types of gravitational waves we are looking for. There are actually mainly 4 types of gravitational wave sources, depending on the signal timescales and how well we can model them. And the chirp signal from the compact binary mergers is the only one type we have observed so far. And we also look for like transient burst signals from events like supernovae, very weak continuous emission from spinning neutron stars, which has very small non-X symmetry. So as they rotate, they continuously generate very weak signals. And also the stochastic background signal from unresolved astrophysical sources like this figure shows here. But in addition to these sources, we actually look for even more exotic astrophysical systems, something like a boson cloud, which might form around the spinning black holes. And these systems are expected to emit continuous waves like those from the spinning neutron stars. And these systems and phenomenon here is basically what I want to cover step by step in this talk. So I'll mainly divide the talk into 4 parts. So I start with an introduction of the background, the ultralight bosons, the superradiance effect, and then some signatures of gravitational wave emitted by these systems. And then I'll discuss some major categories of the astrophysical systems and how well we can search for these systems and our sensitivity. And in the end, I'll present some major results from a couple of recent searches, especially the latest one carried out in the LIGO Virgo collaboration. So to start with, about ultralight boson particles and superradiance effect. So I know there are many experts here, so you probably know this better than I do. The standard model particle physics is very successful, but still incomplete, and especially it's not compatible with GR and do not have viable dark matter particles. There are alternative theories predicting the existence of new particles, including scalar, vector, and tensor fields. There are a few examples here, like QCD axiom is one well-motivated particle to solve the strong CP problem, as you know. There are other examples like a string axiom, dark photon, etc. Because of their nature, for a large parameter space, they can be dark matter candidates. And because of their extremely weak coupling to the standard model, and that's also even model dependent, and extremely small mass, it's very difficult to search for these particles using like conventional lab experiments. However, we now have these gravitational wave observation, and these detectors can provide us with a new approach to look for these particles in the universe, and mainly taking advantage of their universal character of gravitational interactions. The key idea is as follows. So this ultralight boson field around a rapidly rotating black hole can grow exponentially due to a phenomenon, the so-called superradiance. And macroscopic cloud can form around the black hole and generating gravitational waves that can potentially be detected by our detectors. So I know there's a lot of information in this bullet point, but basically that's what I need to explain in detail in a minute. So we search for these particles through gravitational wave data analysis. Ideally, the best scenario is we detect some signals and we detect a new particle. But even without detection, actually by translating the limits on gravitational wave strength, we can derive very interesting constraint on the boson properties. And that's largely complementary to other like lab experiments. So first of all, what is superradiance? So that is actually pretty easy to understand. It's just a kinematic effect. So imagine that we throw some ball tangentially towards a spinning cylinder with some initial velocity vi here. And if the velocity divided by the radius of the cylinder is smaller than the angular speed of the cylinder, the ball gets accelerated and leaves with a larger speed. And in the case of incoming waves, so if the angular frequency of the wave is smaller than the angular speed of the cylinder, the wave is scattered with a larger amplitude. So simply speaking, superradiance is just a phenomenon of amplified scattering of waves. So next, we can actually replace this cylinder with a rotating black hole, and we have some incoming bosonic waves. If the angular frequency of the wave gets amplified, and that means it extracts the rotational energy from the black hole as in the Penrose process. So that is the so-called black hole superradiance. And we listed this condition here. The omega is the angular frequency of the particle, the m is the azimuthal content number with respect to the rotational axis of the black hole, and the omega h is the angular frequency of the black hole's outer horizon. So that is the condition for superradiance to happen around the black hole. And back in the 70s, Press and Tarkowski explored a scenario of a black hole bomb. So if we place a perfectly reflecting mirror, the blue curve here, around a spinning black hole, if we have some incoming boson, incoming waves, and that's satisfying this superradiance condition, and it gets amplified from the black hole and reflected back from the mirror and gets amplified again and back and forth. Eventually that becomes a black hole ball. So that is the so-called superradiance instability. And that basically requires this confinement condition. You have to have this kind of mirror there to trigger this instability. And in the case of ultralight boson particles, because they have very small mass and they feel the gravitational pull of the black hole and tend to bound to the black hole, if the waves satisfy this superradiance condition, and meantime, if the Compton wavelength of the particle is comparable to the black hole size as the condition here shows. So the lambda is the Compton wavelength of the particle with the MB being the boson mass. And this is the black hole size. When this condition is satisfied, these particles are kind of naturally forming a mirror around the black hole, and these waves get trapped in the potential well and grows exponentially. So in other words, the number of particles grow exponentially, forming a macroscopic cloud. Basically, you can see we will need like a superradiance condition and the confinement condition to be both satisfied, and we need a rapidly rotating black hole, and we also need to have some kind of matching condition to trigger this instability, so the system can produce some potentially observable signature. So in that sense, actually nature provides us with a lab full of astrophysical black holes, and accordingly we can probe these boson particles in a corresponding mass range that can trigger this instability. So that's corresponding to roughly 10 to the minus 20 to 10 to the minus 9 EV. It's a very interesting parameter space. Before talking about observational signatures, we can take a further look at this black hole and boson system. So basically, if we solve the Schrodinger equation over a curved background, we can get the energy levels indicated by this equation. And this n bar is the principal quantum number, and this alpha here is the fine structure constant. And this looks really familiar, right? It's basically like a hydrogen atom, and even the definition of fine structure constant is similar to what's defined in the hydrogen atom. Although there's also difference here, obviously this system is non-Hermitian because of the ingoing boundary condition at black hole's horizon, and these particles are bosons rather than fermions. So eventually, what happens is in this huge black hole gravitational atom, the occupation number for a given quantum state can grow exponentially, and one energy level dominates at a given time. So that is the overall picture of this superradiance phenomenon. So keep that in mind, we can actually discuss the features of gravitational waves emitted by these systems. So once the energy levels in this huge gravitational atom is kind of populated, there are 3 different mechanisms generating gravitational radiation. So the first is called annihilation. That's basically 2 bosons annihilate into a graviton, just like an electron and positron annihilate into a photon. And the second is called level transition. So the bosons can jump in between the energy level, just like the electrons jump in the hydrogen atom. Oops, sorry. Is that a question?
I think someone was unmuted. But,
no problem. I'll just continue. So yeah, so the level transition is similar to something like the electrons jump in the hydrogen atom. And the third one is called bosonova. That's kind of the collapse of the cloud because of the self-interaction of the particles. So these different mechanisms generate gravitational radiation in different ways. They have different features, but from observational point of view, the bosonova signal is generally too short. It's like a burst lasting for milliseconds. It's very hard to model. And also it will require quite a strong particle interruption. Like for some instance, we don't even expect that to happen. Like for QCD axiom, that's probably not the case. And then for level transition, that basically require more than one level to be occupied with considerable number of particles so that the signal would be richer and observable level. But that could take like thousands of years to get there after the birth of a black hole. So that would be too weak for young black holes. And on the other hand, the duration of such signal is generally short. So it's also very difficult to look for these signals from older systems. Then the most interesting one is annihilation. So because of this extremely large number of particles in a single energy level, the emission is like a coherent and a monochromatic, just like the continuous gravitational waves emitted from spinning neutron stars. It's very similar in the signal morphology. And we mainly are interested in searching for these sources. And from the search point of view, we are more interested in the fastest growing level and the dominant level of a scalar field. That is like it forms the fastest and it produces the strongest signal. And the quantum numbers are listed here, but for the rest of the talk, I mainly focus on this mechanism and this scenario. So we can take a further look at the whole procedure and try to understand it in a classic way. So when a black hole is born with some spin, so as a result of either a stellar collapse or merger of binaries, then the quantum fluctuation will cause these pairs of particles to spontaneously appear in the vicinity of the black hole. And if the superradiance condition is satisfied, these number of particles start to grow, extracting energy from the black hole. And if the confinement condition is also satisfied, basically the Compton wavelength of the particle is comparable to the black hole size, then the black holes start to kind of resonate with the field, and the field grows exponentially. So the number of particles grows exponentially and forming such cloud around the black hole. And the particles in the cloud annihilate into like gravitons and generating gravitational waves. And this kind of cloud will keep growing until at some point the significant amount of black hole's rotational energy is extracted. And then you can see this condition is no longer satisfied as the black hole is spin down. And then superradiance will shut down at that point. That is, usually we say that the cloud is kind of saturated. Just to give you a sense of the numbers, so the number of particles occupying a single energy level can reach 10 to the 77. And in an optimal case, the cloud mass can reach about 10% of the black hole mass. So that's a significant amount of energy. And the size of the cloud really depends on the fine structure constant alpha. So if it's in a very small alpha region, then the cloud is larger. But if it's on a fiducial value about 0.1-ish, that's kind of tenths of the size of the black hole. Because we are considering this fastest growing scalar level here, actually this shape of the cloud is like a dumbbell. It's not a donut around the black hole. So once the superradiance is shut down and then the cloud is co-rotating with the black hole. So you can imagine it's like a rotating binary system, and that emits gravitational waves over a very long lifetime. And the angular frequency of the wave would be twice the angular frequency of the particle. And emission is continuous and monochromatic. We do have a very small evolution term here, a very small positive f dot. That's because as the cloud dissipates and shrinks by emitting gravitational waves, it's like a shrinking binary system, so the frequency gets higher. Or in the other way to think about that, because the cloud emits gravitational waves and the total mass of the system is decreasing, causing the negative binding energy to increase. and then the energy level, the energy of these particles slightly increase and causing the emission at a slightly higher frequency. But this is a very small effect. And then after a very long lifetime, like millions of years, eventually the cloud will completely gone and leave behind a spin down black hole. That's kind of a simplified picture, although there are more complicated situations and like different energy level and things like that. But that's just a quick introduction of everything here. Then for gravitational wave searches, we want to know like what parameter space we actually want to focus on. So given a black hole with some non-mass, then as discussed earlier, only those bosons actually falling in a mass range that correspond to the black hole mass can satisfy this confinement condition indicated here, so that to trigger the instability. And like at the first place, the superradiance condition needs to be satisfied. That means if we have a black hole spinning slowly or it's not spinning at all, superradiance is not happening at all. So based on these conditions, we firstly can derive like the range of this fine structure constant alpha, which defines the relation between the black hole mass and the boson mass. And this is basically a small number and in a small range. So at this point, we can see that there's kind of a matching relationship between the black hole mass and boson mass. So according to the black hole mass range that is sensitive to the ground-based gravitational wave detectors and the space-based detectors, we can probe different boson mass range accordingly. So for example, for the LIGO detector, we are sensitive to the range about 10 to the minus 14 to 10 to the minus 11 eV. And for LISA, which is designed for higher mass black holes, so we can actually go to a lower boson mass range. And then the other interesting thing is, as mentioned earlier, the gravitational wave emission frequency is determined by the particle's energy or particle's mass. So that means for a given black hole, we can actually estimate the range of boson mass and the emission frequency of gravitational waves. This equation here gives a rough estimate of the emission frequency. So for the fiducial value of alpha and 10 solar mass black hole, it's emitting at 100 Hertz band, which is the most sensitive band of our current detectors. So that's really interesting and a clean scenario. So shortly speaking, for a black hole with given mass, it kind of resonant with bosons in a narrow mass range, and then emit gravitational waves at frequencies in a limited band. So from the search point of view, we know what parameter space of these particles we can actually probe given a black hole, and what frequency band we can search in depth and try to get the best sensitivity out of that. A bit more information about the signal timescale. So here we are still considering the fastest growing scalar level, and we consider a particular example with the black hole mass being 60 solar mass and spin 0.7. That is similar to a remnant black hole formed in the first gravitational wave event, the GW150914, which is a merger of two black holes with about 30 solar mass each, and they form a new black hole about 60 solar mass. So that is quite typical LIGO Virgo detections. In this case, the vertical axis stands for the time scale on the order of in the units of years. Horizontally, that's the fine structure constant alpha, with the definition here, and the corresponding boson mass. There are two curves. The orange curve stands for the time scale for the cloud to grow, for the superradiant instability to happen. And that's on the order of months to years. So that's really a very efficient effect. And that's negligible compared to the lifetime of the black hole. And then this purple curve is on the order of 10 to the 4th to 10 to the 7th years. So that's really the the time scale of the emission of gravitational waves. And that's why it's considered as continuous gravitational wave source. It's always there. And this dashed line here indicates the optimal matching scenario where this phenomenon is maximized. Okay, so this is the overall picture about how gravitational wave is generated and what parameter space we are interested in. And next we can take a look at the typical like astrophysical systems we usually want to search and our sensitivity. That can mainly divide it into 3 categories, and they all have different advantages and disadvantages. So I briefly go through them one by one. The first type is the remnant black hole formed in the compact binary mergers, like those ones detected these days. So that is a really interesting type of sources we want to focus on. Obviously, it has well-known age because we detect them in the gravitational wave channel. They have well-constrained sky position, mass, and spin, these properties of the black hole. And they have clean environment because they are newly born. But there are disadvantages, like the existing detections are generally too far away for our current detectors. The reason is the signal from the boson cloud formed around the remnant black hole would be much weaker than the merger system itself. So our detectors right now are sensitive to the merger events, but still not so good for searching for the boson cloud, which are expected to form around those remnant black holes if the right boson particle exists. Overall, this detection or analysis will be more promising with the future detectors. But again, this is a very interesting scenario. Second is the black hole in X-ray binaries. They are much closer and better localized because we have the EM observation. But there are problems with these systems in the analysis. For example, their age and history are largely unknown, making it difficult to interpret the superradiance scenario. We don't really know like what stage the system is in if superradiance is happening. And also the uncertainty of spin measurement for X-ray black holes is pretty large, and superradiance actually quite strongly depend on the spin of the black hole. And also we don't fully understand whether the active environment of accretion impacts the cloud if the cloud exists, although we don't expect that to have a strong impact, but there could be some unexpected impact on the signal signatures. And the black hole mass is relatively lower, so the emission is towards higher frequency where we are less sensitive to. And also there are technical challenges to search for black holes in binary motions because of the orbital Doppler modulation. And we will get to that in more detail later when I talk about the search and analysis. And the last category are the isolated black holes in our galaxy. They are also close. They have cleaner environment compared to the X-ray binary black holes, but their locations are unknown because we don't observe them in EM observation. So we basically need to run an all-sky gravitational wave search and looking for any possible emitter from the galaxy. And if we don't detect a signal, that will we will have some difficulty in interpreting the results, like which might rely on the assumption of black hole population and black hole properties like age and spin. I'll also give more explanation about this later. So among these 3 categories, the first one is still the most interesting and ideal targets to follow up. I'll give a bit more detail here. So first of all, we witness their birth in the gravitational wave detections. So that actually gives us some hints of when is a good time to follow up these systems, because we can roughly estimate like the time scale for the superradiance to happen and when the signal might reach the maximum, things like that. So one possibility is like to follow up one remnant black hole in the next observing run for the events that was detected in the previous observing runs, things like that. The second thing is we have well-constrained sky position from the gravitational wave observation, especially now we have the network of detectors. That is important for the long duration signal searches because we need to integrate the data over a long time, and we need to carefully calculate the antenna pattern as the Earth moves around the sun and Earth rotating itself. So the accurate and precise position in the sky would be important for the long duration follow-up. And third, they have well-measured mass and spin from the parameter estimation of the gravitational wave event. That actually gives us additional information like what parameter space we can focus on and put most of the computing resource into that narrow range. As explained earlier, we can predict like what is the most interesting boson mass range and corresponding emission frequency and things like that. And also because the signal morphology is so similar to the continuous waves expected to emitted by neutron stars, we already have quite many mature methods that are ready to be applied to this kind of new systems. And using those methods, we can even estimate like how far away we can reach, whether this is a good event to follow up and things like that. So we have carried out some Monte Carlo simulations based on like very accurate waveforms and using the real like search methods to estimate how far away we can reach such signals from these boson clouds if they exist. So in this figure, the colored contours stand for the horizon distance in units of megapasecond, or in other words, the largest distance we can reach for these systems as a function of the initial black hole mass on the horizontal axis and initial spin on the y-axis. I mean, by initial, I mean the mass and spin after the burst of the black hole. And then these white contours stand for the corresponding boson mass in the units of EV. Then this is assuming that we use one advanced LIGO detector at its design sensitivity and observe for a whole year. And to give a more concrete example, this star stands for a black hole with 60 solar mass and 0.7 spin. That's kind of the remnant black hole of GW150914. And for that kind of source, we might reach about 10 megapasecond, while the real event actually happened 100 megapasecond away. You know, so although like using more detectors, like the network of detectors, and extending the observation time can further improve our sensitivity and we can reach further. But, you know, one order of magnitude is still kind of beyond the reach of current generation detectors. But things will be very different if we have future generation detectors, the next generation detectors, which are being planned and being designed. Like Cosmic Explorer is expected to have arm length of 40 kilometers. That is 10 times the arm length of Advanced LIGO. Then for the same event, we can reach 160 megapaseconds, still assuming one detector and 1 year's observation. And of course, we can reach further by using more detectors and observing longer. And that will become reachable. And also there's a more interesting parameter space going towards higher mass black holes and higher spin, and we can even reach 1 to 2 order magnitude away. So generally, things will be more promising with the next generation detectors. But that being said, in the existing runs or the upcoming runs, if we do have very interesting event, for example, a merger happened relatively close and they have well-measured parameters, well-constrained sky position, we will need to like look into the data anyway. Unfortunately, in the last run, 03, we don't have particularly interesting candidate to follow up, but we hope to have some interesting events to take a look in the upcoming run, which is now planned to start in the end of the year. But generally, instead of waiting for a perfect event to happen or wait for the construction and operation of the next generation detectors, we can actually already started doing a lot of interesting studies using existing data by studying black holes, which are nearby. So that's basically the last part I want to cover in this talk. Some major results we obtained from the recent analysis. So first of all, I'll explain results from a directed search targeting a non-black hole, Cygnus X1. So by directed search, I mean, we have a particular target, a non-black hole to look at. So we do not rely on any black hole population assumption or on some unknown properties of these black holes, because we know what we are looking for. We know the mass and a lot of information. There are quite many nearby X-ray black holes, but we selected Cygnus X1 for a few reasons. It is actually considered one of the most interesting sources for studying superradiance. First of all, it has relatively high black hole mass in the X-ray black holes. So the emission frequency will be in the more, like kind of the most sensitive band of our detectors. And it's very close to Earth, only 1.86 kiloparsecond. It also has relatively well measured optical parameters. So why does that matter? I put this animation here, as you see. Basically, we are looking for the monochromatic signal emitted in the vicinity of the black hole if the cloud exists. So this signal itself is almost monochromatic, but the black hole is in this binary motion with the companion. So you can imagine there's Doppler modulation caused by the binary motion. And we have to account for that, and that rely on parameters like the optical period, the semi-major axis, and things like that. Cygnus X1 has relatively well measured optical parameters and compared to the other X-ray black holes, but still the precision is not good enough. So what we actually did is to search over a parameter space, although relatively narrow, of these optical parameters to make sure our search is sensitive enough to cover cover the uncertainty of these parameters. So we looked in the second observing run of Advanced LIGO in the frequency band of 250 and 750 Hertz. Unfortunately, there's no interesting signal candidate, and we don't have any detection, but the results can be interpreted under different scenarios. So first of all, in the first scenario here, we assume that the bosons do not self-interact significantly. That would be the case like QCD axiom. In this figure, the y-axis stands for the signal strength, and the horizontal axis is the emission frequency of the signal and corresponding boson mass on the top, because we know the mass of the black hole. And then this black curve indicates the upper limits obtained from search. That means if we have a signal, if there exists a signal louder than this level as a function of frequency, we should have already see it in the data. But because we don't see it in the data, that's the upper limit. And the colored curves here stand for the expected signal strength under two different assumptions of the black hole age. So the thicker curves stand for an old black hole for 5 million years old, and thinner ones stand for 100,000-year-old black hole. That's easy to understand if you have some black hole which is really old, and even if the cloud existed, it has spent a very long time dissipating, and this emitting signal would be much weaker. And for a younger black hole, then the cloud is younger and the emission is stronger. And the color on these curves stand for the fine structure constant alpha. And you notice that these curves both turn at some point. That's because for more massive bosons, the decay rate would be higher, so the cloud dissipate quicker. At this point, you can see that the results actually strongly rely on the assumption of the black hole age. So that's why the uncertainty of the black hole age would lead to a large uncertainty on the constraint. Basically, by comparing the expected signal and the upper limit, where the expected signal is louder than the upper limit, that's the disfavored boson mass range, as we don't see the signal, so indicated by this gray band for these two scenarios. So there's also another caveat with this scenario. So we actually do not rely on the spin measurement of Cygnus X1 here, and assume that the spin of the black hole after the superradiance is a free parameter. So there's potential conflict here. We know that although there's large uncertainty in the spin measurement of X-ray black holes, but Cygnus X1 is generally believed to be a high spin black hole. It's old and it's still spinning fast. So you might imagine like the superradiance might have never happened and the cloud have never existed. So that's one potential problem. And also because we don't really know the history of the system, so that makes it difficult to interpret. So we actually studied a different scenario where the nonlinear self-interaction of the particles have been taken into consideration. So that would be the case for string axiom. So this scenario can be explained by this diagram taken from this paper. So basically there's some scalar field growing due to superradiance, and at some point it reached a level of decay constant around this decay constant Fa, and then the nonlinear self-interaction of the particle is strong enough to trigger the boson nova, and part of the cloud suddenly collapse and releasing a burst of gravitational waves, and then the field drops. And then superradiance starts again and back and forth. So the superradiance is never saturated. That would allow and the cloud to exist around an old but high spin black hole like Cygnus X1. But note that here we are not looking for these burst gravitational waves. We are looking for the continuous waves over the long lifetime. And there's also one caveat associated with this scenario. Here in the search, we do not take into consideration the possible oscillation in the radial direction of the cloud because of this periodic process. Although the effect should be quite minor compared to the overall signature of the signal, but more accurate study would rely on further numerical study, but we do not take that into consideration right now, but the search is potentially can be further improved when the future more accurate numerical results is available for this scenario. So the results can be interpreted here. In this case, the decay constant Fa and the boson mass are two independent parameters, so we put them on two axes, and this is the corresponding emission frequency. The colored contours stand for the expected signal strength calculated from the theory in this scenario, and these black dots are translated from our upper limits, and the shaded region is excluded because we don't see the signal in the data. That's basically for decay constant around 10 to the 15 GeV, and then this range is disfavored. And the white parameter space is where the condition for boson nova to happen is not satisfied, so we cannot apply this scenario here. Okay, so this is the main result from this directed search. So next, quickly explain another type of scenario, which is the undirected search, basically all sky search for any possible emitting boson cloud out there in the population. So first to show this figure taken from this paper, and they actually estimated the number of detectable signals as a function of boson mass, if they exist, and the corresponding gravitational wave frequency. So there are different markers basically stand for the different assumption of maximum black hole mass and maximum spin in the population. So generally you can see for more massive black hole with higher spin, there's a better chance to see those things if the right boson particles exist in this mass range. But the takeaway message here is if there exists boson in this kind of mass range, in our universe, in our galaxy, by searching the data like in the existing detectors, the existing observing runs, we already have pretty good chance to detect these signals if they are out there. So this is based on the sensitivity of Advanced LIGO in the first observing run, but actually the sensitivity is upgrading run after run, so it's getting better. In the latest observing run 03 within the LIGO Virgo Kagra collaboration, we carried out the very first search, a tailored all-sky search for these scalar boson clouds, looking for these individual signals emitted by these clouds in our galaxy. There have been previous undirected analyses. For example, a group of people have searched for the stochastic background from these scalar boson clouds, but that is not looking for individual signals. It's like for the background from unresolved signals if they exist. And also there have been constraints directly translated from the pre-existing all-sky continuous wave searches. Those are also different because the previous continuous wave searches are designed for continuous wave from spinning neutron stars. Although the signal morphology is very similar, but the parameter space is slightly different, like the spin up range or spin down range. And then these constraints are actually not optimized for these systems. And this search we carried out in the 03 run is the first search customized for the scalar boson clouds, and all these configurations and parameter space optimized for these signals. And we looked into the data collected by Advanced LIGO and in a pretty wide band, 20 to 610 Hertz. But again, we don't have any surviving signal candidates or anything like regarded as interesting, potentially real signals. But we still can translate the results, the constraint into some constraint or on the boson properties and things like that. Although the scenario here would be more complicated, I'll show a few examples here how we interpret the results. So first way is that we can derive the disfavored parameter space for the boson mass versus the black hole mass. So because this matching relation between the boson mass and black hole mass for this superradiant instability to happen, and because we don't see the signal in the data, the shaded region is basically disfavored, and the darkness is based on different assumption of the black hole age. That's easy to understand. For an old black hole, the expected signal would be weaker, so the disfavored parameter space would be smaller. And on the left and the right, they are corresponding to the assumption of a closer distance and larger black hole spin, and larger distance and smaller spin. So again, this is kind of an optimistic scenario. So this expected signal would be stronger and larger parameter space is excluded, while this one, we can only say something about a smaller parameter space. Alternatively, we can derive the maximum distance we can reach as a function of the boson mass. So here, the left and right plots stand for different assumption of the maximum black hole mass in our galaxy, cut off at 50 solar mass or 100 solar mass, and we assume this mass distribution relation here. But generally, the mass distribution here does not have a significant effect on these constraints, but the more significantly, these different markers or different curves come from different assumption of the black hole age. So again, for older black holes, the emission is expected to be weaker, and we can only reach for a very small distance. But for younger things, we can reach larger distance. So one way to interpret that is that because we can reach tens to 100 kiloparsecond, if the boson cloud younger than 1,000 years exists, we should have seen it in the data. I mean, in this mass range. So that's not likely to exist in our whole galaxy. Now you can see that without the detection, the constraint or the conclusion obtained in all sky search is pretty complicated, basically rely on all these assumptions of the population and unknown properties. So that's why following up a particular black hole with known properties would be very interesting. But overall, carrying out these all sky searches are interesting and important because that gives us the chance to detect these signals if they do exist, just using our existing data and existing detectors. So I'll just quickly summarize here. The gravitational wave detectors provide a new way to search for these new particles. And we have been carrying out both direct research targeting a known black hole and all sky search for any possible emitters out there. The newly born isolated black hole would be quite ideal target to look at, but that would be more promising with future detectors. And so far we have been talking about a scalar cloud, but vector and tensor fields can also generate such signal, but with stronger signal amplitude, but shorter time scale. There are already some methods to look at these signals, but the development of optimized search strategy is still a work in progress. So for the future, it's very interesting to combine these different studies like theoretical predictions, gravitational wave search results, and constraints from other analyses. So I would really hope that I have more chance to talk to some of you and look into the possibility of new studies in the future. So that's all I want to share today. Sorry, I probably take a bit longer than I expect, but thank you all very much for the attention.
Thank you very much. Yeah. So yeah, let's have some questions. Anyone have any questions they want to ask? Please just go ahead. Maybe I can start. Can you go back to the plot where you showed the constraints from Cygnus X1? I think it's that one there. The one.
Yeah, this one or this one.
Yeah, this one. Yeah. So what are the so okay, if I interpreted this correctly, the constrained region is like the stuff that's kind of shaded brown between the kind of the smooth black curve and then the data. Is that
yes,
right? Yeah.
Yes. So this region is excluded.
Yeah. Okay. And the gaps in the data, what are they, sort of instrumental lines or something?
Yeah, that's a good question. So those are actually the bands which are basically contaminated by instrumental lines. So we cannot really see anything in those bands.
Yeah. Okay. So I have a sort of I think a very naive question, which I think probably reveals my ignorance for how gravitational wave observations work. But you use the language of sort of search and observation, and as far as I understand, these instruments aren't things you can like turn and point at particular places in the sky. What does it mean to search for something in gravitational wave?
Yeah, that's a good question. Yeah, it's true that gravitational wave detectors are not like telescopes you can turn around like pointing towards a direction in the sky. But maybe the language is kind of a jargon in the gravitational wave world. So we say we run the search targeting a sky location, which means we account for the all this motion of the Earth. For example, it goes around the sun and it rotates, and then this the orientation of the detector change, the antenna pattern changes. So all these things are correctly accounted for. And then if the sky location is not correct, you are actually applying a wrong, for example, Doppler modulation correction, and then that impacts the sensitivity. So when we say we direct or target some particular sky location, we mean we use that sky location to correct for the Earth's motion.
Yeah, I see. Okay, so it's all happening after the data's been taken. You're just analyzing it in a different way.
That's right. Yes. Yeah, exactly.
Yeah. Cool. Okay. Does anyone have any other questions? I'll allow it. I feel like the students should, because there is the competition going on for the student who asked the most questions. But maybe I can ask a different one. So this issue with the could you go 2 slides to slide 26? Because this issue with the source age, you've sort of just chosen 2 reasonable values there. Do we have any handle on that? Because it seems like quite a big uncertainty, which I guess if it was really bad, you may not be able to set a limit at all if you really had no other kind of way of getting some access to this source age. Can you talk a little bit more about that?
Yeah, that's right. This is one difficulty we actually found when interpreting results for a black hole, which we don't really know its history, but we looked at the literature, and there are different analyses and different studies to predict to estimate the age of the black hole. So we actually take one kind of optimistic case and one towards the other end. It's kind of under different, using different methods and under different assumptions. And also another interesting thing I forgot to mention here was, I guess people have been asking whether the accretion effect actually helps to keep the black hole spinning fast and keep the cloud exist for a longer lifetime. But actually the efficiency of accretion is much lower than efficiency of superradiance. The superradiance, as I showed earlier, can goes like months to years, but accretion is on the order of million years, I guess. It cannot really be a significant amount of something adding to the black hole spin and keep it spinning fast and keep the cloud growing.
I've got a question. It's Roland here, Lily.
Yeah.
I'm just wondering, I mean, if you could somehow have perfect knowledge of the distribution of the masses and the spins of say the black holes in the galaxy, I mean, would you expect that if there really were these ultralight bosons, that there would be, for instance, there would be upper limits on the spin parameter as a function of mass or something like that? Would there be that you just wouldn't expect to find black holes, with spins greater than some number?
Yeah, that's a good question. Actually, there have been studies even before these gravitational wave searches. People have been just using the spin distribution of the black holes to derive the constraint on the boson properties. Like if these types of boson do exist, so we actually don't expect a particular mass of black holes, they spin very fast, right? So people have been doing these studies, and even with the gravitational wave detections, like all these Virgo black holes, and people are also studying the spin distribution of these black holes and see whether they exist or not. But that, so first of all, the spin measurement is generally not so accurate. Both in the EM observation and in gravitational wave observation, the spin, there's always very large uncertainty in the spin measurement. So that will lead to large uncertainty of the constraint as well. And also, there are some more complicated effect, I think, affecting these constraints derived from the spin distribution. And while looking for the gravitational wave signal itself, it's a more direct way kind of to if we want to say we detect something, that has to be something observed.
Mm-hmm. Okay, thank you.
I have a question.
Yeah, sure.
I'm a student, so I'm not sure if this question is a bit too simple and naive.
No, there's no simple and naive question. Thanks.
So for the superradiance and then boson waves, why do only ultralight bosons, wouldn't like other bosons that we already know exist produce this effect, or is it because the mass is too high that it's not possible?
Yeah, that's an interesting question. So, right. So basically, if we imagine like really massive bosons, that would be like interacting maybe with very small black holes. I think that's generally already kind of below the black hole mass range, right? So far we don't see black holes below 5 solar mass. So I guess if you are talking about like 10 to the minus, above 10 to the minus 9 eV, and that's something too massive to interact with any non-black hole.
Okay, thank you.
All right. Is there any more questions? Maybe, yeah, I did have a few more questions. What would be the more interesting one? I guess you mentioned very briefly at the end there the constraining not just scalars but like vector bosons, tensors. Can you go back to this the slide, the summary slide that you had, because you made a statement there. You said the development of the search strategies is a work in progress. Well, I'm not entirely sure why you would need a different search strategy for them if it's just a matter of the signals like a different amplitude and a different frequency. Can you why is the search strategy need to be different?
Yeah, yeah, how to say that? Actually, it's not like a same type of signal. So it's not like in the case of vector, and I guess there's not much study for the tensor fields right now. So far, there's some work on the vector field side. I guess tensor field is more complicated. That will also involve some like modified gravity and kind of thing. But for the vector case, the signal is generally much shorter. So for scalar boson cloud case, we can regard that as continuous waves, and the signal strength doesn't change over the 1 year, 2 years observation, and frequency changes only slightly. But for the vector case, it actually spans a very wide parameter space, even for the frequency evolution and the amplitude evolution. So in some extreme case, it could just evolve over a few hours. So it would be more interesting in that case. For the vector case, it would be more interesting to look at newly born black holes like the remnant from the CPPC mergers. And because right after the merger, we should searching the data, right? For old black holes, it's not likely to be an interesting source. And then these signals are extremely short. So it's kind of, you cannot just assume it's monochromatic signal is simpler. You can integrate the data over the long time and like coherently even. But for the faster evolving signal, it's kind of, you need to take into consideration like F dot, F double dot, and all these things.
Yeah, that makes sense. Yeah. All right. So if anyone has any more questions, they're free to ask them. Roland?
Well, what about speaking about other more massive bosons? What about these clouds around primordial black holes?
Yeah, I guess that's an interesting question. Like, I guess the problem is we are also looking for primordial black holes. I guess there's another uncertainty there, right? If the primordial black holes, they do exist, or we observe them, or how far away they are, and the properties of these black holes we don't even know. Like, do they spin? So all these things are larger uncertainty. I guess maybe towards higher mass range, it's also possible to be probed with like lab experiments. So it's not like it's completely not possible to reach. I think there's some overlap between the different methods.
Cool. I just see that so if you had a Higgs boson, the Compton wavelength would correspond to the gravitational radius of a 10 to the 12 gram black hole.
Wow.
If I get that right.
I think that would evaporate before today, I think, wouldn't it?
Okay, all right.
Oh, before today.
Yeah.
All right.
Roland, I can certainly talk to you sometime
Good. Yes.
on Stromlo or somewhere.
Yeah, sorry.
All right, well, I'll stop the recording there.